Okay, so here we are in VS Code. I have VS Code opened on my own copy of my work directory, and you should pause the video at this point and go ahead and open up your own my work directory. We have some files that we've worked on. I've tucked away some old files in my old directory. I've got some other stuff in my new directory for future work. You should be seeing something like this here. Our goal is to implement or to write a, I'll call it an implementation. You could also call it an executable specification of the syntax and the semantics of propositional logic, the language that we just discussed in the last lecture video. So we're going to do that in the usual way. Within the source directory, I'm going to create a new file, and I'm going to call this pexp.lean for propositional logic expression. Yeah, that's fine. Okay, and I'm also going to create, this is the file in which I'll write my specification of the syntax and semantics of propositional logic. And as I write this specification, I want to kind of test out what I've written, so I'm going to create a second file called pexp_test.lean. And in the px_test.lean file, which is now open on my screen, I will import .pexp from the current directory. So definitions that I write into my pexp file, which I've now selected, will be imported in the pexp test file so that I can kind of develop my specification and my tests of this specification at the same time. Now, I want to develop this specification in which, as I said before, I'm going to leave certain holes for you to fill in, but I want to develop it in a very step-by-step kind of incremental way to reinforce fundamental concepts of the separation between syntax and semantics, the organization of a syntax in terms of literal, variable, and operator expressions, to make clear why we write certain constructors the way we do, how case analysis works, and essentially to make sure that we're covering fundamental concepts that you should be remembering and that you should remember into the future. Okay, so here we are. Let's get started. Here we are in our pexp file, and let me make a little bit more room on the screen here. What I think I'm going to do is put my test file on the right-hand side of my screen. You can use view, editor layout, and split your screen up, down, move tabs left, right if you want. Here we go. I'm going to close out my terminal window, and I'm going to close my project browser window on the left because these are all the files that I'm going to need. So on the screen now you can see the complete setup that we have. pexp.lean on the left, pexp_test.lean on the right. The test file imports the file on the left, and we're ready to go. Okay, so let me start by adding just a couple of comments. We're going to implement the syntax, and we're going to implement the semantics of our little language. Okay. Now, we define the syntax of a language by defining a data type. And again, the values of this data type will be the terms, the expressions in our language. So let's start super simple. Let's define a piece of propositional logic, a language with just one literal expression, literal true. Inductive, and I'm going to call the type of logical expressions pexp for propositional logic expression, just like we used bexp for Boolean expressions, axp for arithmetic expressions. Here I'm going to have a type specifying propositional logic expressions. So this is a type. And for now, the syntax of our language will just have one term. I'll call it ptrue, and that all by itself is going to be, is thereby defined as a value of type px, which is to say a term or a sentence, if you will, an expression in our implementation of the syntax of propositional logic. Now, that's all well and good, but before we develop the rest of our syntax, which we could do here, let's actually build and specify the semantics of this language that we've written so far. The kind of semantics that we've been defining in this class is called an operational semantics. And an operational semantics is generally defined as a function that takes a syntactic expression and possibly other arguments. Later on, we will include an interpretation as an argument, but for now we won't. So we're going to write a semantic evaluation function that takes any term in our language and returns its meaning in the corresponding semantic domain. Now we know that the semantic domain for propositional logic is Boolean algebra. P-true is a syntactic term that is meant to evaluate to the Boolean value true. So we're going to build our semantics now, and we're going to specify our semantics as a function. So we will define a function called p-eval, p-eval, o-evac, from o-evac to p-eval, and p-eval will be a function that takes any propositional logic expression in our language and returns a Boolean value. So that's the type of function that we need to implement a semantics for this little language. Okay, and now all we need to do is to define how this function works when given p true as an argument. So we're going to define this function, the behavior, what this function does, in terms of a case analysis. When given a value of type px, well, we need to ask what kind of value did we get. There's only one case to consider. The only case to consider here is that we got p true, and in that case, what do we want to return as the semantic meaning of that literal syntactic expression p true? Well, we want p true to be the piece of syntax whose meaning is Boolean true. And so there you go. Okay, so that's it. If you're not quite sure about how all of this is going to work, just stop the video here and look at what we've done. It's beautiful. It's 4 lines of code that defines the syntax and semantics of a little language. Happens to be a language with just one term, but that term has some resonance with us because, we understand we're defining a syntax for propositional logic. And this language has a semantics that maps every possible expression in our language, of which there's only currently one, to a corresponding value in the algebraic structure in the semantic domain of Boolean algebra. Okay, cool. Okay, so why don't you take a second, and then I'm going to come and do it, and go ahead and add a second literal expression, p false, and then update or extend the semantic definition of this language, okay, so that every term in this language has a semantic meaning. Go ahead, pause the video, you do it, and then start it up again, and you can see me do it. Good. Okay, so we're going to add a second literal term to our language. We'll call it p false. This is a piece of syntax. In other words, a parameter-free, which is to say a constant value of type px. Okay, it's a second term in the syntax of our language. And now, we have a little problem here, right? We expected that we would have a little error here because p-eval needs to be defined for every possible value of this type, but we're not seeing such an error. The reason is that p-true here could be any name, okay? Because p-true here is not the same as p-true here, because of scoping. So if we open pexp like that, now this p_true is this p_true defined in the namespace of the pexp type, as we've discussed many times. And now we get the error that we expect, non-exhaustive match. The following cases are missing. Right? We're defining the meaning, the purpose, the function of p_eval by cases. Given an expression of type pexp, if it's p_true, we return true, but we have no definition for what to return when it's p_false. And there you go. Okay, so now we have a richer language. In fact, we've doubled the number of expressions in our language from 1 to 2, and we've given a corresponding semantics to that second term. So over here now, let's switch over to the test file where we can try out what we've implemented. So for example, we ought to be able to evaluate now the application of the p_eval function to any term of type pexp. Aha, there's a little bit of a problem here. We have another scoping problem, unknown identifier, open pexp. We have to do that here. We do it here in this separate file, and now we can evaluate pexp, and that evaluates to true. And we can evaluate p_false, and that, as you expect, evaluates to false. Okay. We can, well, there's not much else that we can do at this point. This is a very, very simple language. Now, before I go any further, I want to actually do some refactoring, as they call it, some sort of restructuring of the code base here to make it just a little bit more elegant. And the thing that I notice here is that these two constructors are meant to implement the literal expressions in our language. Okay? And then these are the rules for evaluating literal expressions. Okay? I'd kind of like for there to be one constructor to build either of these two literals. Okay? And so what I'm going to do is I'm actually going to comment out what I have here in favor of the following single constructor, lit. But now lit takes a parameter b of type bool, and the value of this parameter tells me which of those literals I'm constructing. Either a literal that should evaluate to true or a literal that should evaluate to false. Okay, so lit applied to true gives me the literal expression, a syntactic piece of a string, if you will, like lit TT is the literal expression for true, and lit FF would be the literal expression for false. And so lit TT or lit FF are both now values of type. Those terms, those two-part terms like lit TT, those terms are values of type pexp. They are syntactically valid expressions in our language. Of course, now our implementation of the semantics is not correct because now there's only one possible case here, not two, but that case comes with a parameter. So the only possible form of an argument of type pexp, given the syntax as we've defined it so far, is that it's lit followed by a Boolean value b. Okay, and in that case, if we get a syntactic term that looks like lit b, what do we want to return as the corresponding Boolean meaning of that literal term? Why, it's just b. Okay, and so in this way we can take this sort of more complex but more straightforward implementation of the literal terms in our language and replace it with a kind of cooler and more elegant implementation with just one constructor for any of the literal terms in our language, like that. Okay, so I'm actually going to delete these intermediate states of our development, and in fact I'm going to take out the comments as well here so that we can really just focus in on what we've got. Okay. Now let's look over here in our test file and make some fixes here. So we're going to comment out, maybe I'll leave these comments in, we're going to comment out the original expressions that evaluated our literal expressions, and what do we replace those with? Well, we evaluate the application of p-eval, and in parentheses here I'll put an underscore, and of course what we need here is an expression in our language, an expression of type px. And the only expressions we can build right now are literal expressions, and the way to build them is with the constructor lit applied to one argument. Okay, and that argument, as stated here, needs to be a value of type bool. Lean tells us, of course, that we need to fill this hole with a bool, and so we fill it in with a bool. So there we go. Okay, and this expression, lit_tt, is an expression in our language representing the literal true value. Okay, awesome, good. Okay, and as expected, this expression evaluates to, or has as its semantic meaning, the Boolean value true. And sure enough, if you write the second test case and put ff here, then this will evaluate to ff. So as a reminder, let's just sort of remember, let's look at how this expression gets evaluated. The application of p-eval to lit_tt. P-eval is given an expression px, which in this case is lit_tt. Lit_tt matches with this pattern lit_b, where b is bound to tt locally within this rule. Given that match, we simply return b. Okay? So you can think of this pattern matching construct as essentially taking this expression and breaking it up into its pieces. One piece is the lit, the second piece is the b, where b is bound to tt, and in that context, where b is now temporarily bound to the Boolean value tt, we just return b, and that does the job for us. Okay, cool. Now, I do want to introduce one new construct in Lean that you haven't seen before. We haven't emphasized it, but I spoke to it in the introduction to this this pair of lectures, and that's the notion of concrete syntax. So this expression right here, lit_tt, is a term in our language, and it's meant to represent the literal expression true. Now, if you think about Python or Java, right, there's a literal expression for true in those languages. It's true, and so you can write an if statement in Java. You know, if true and something else, then blah blah blah. Okay, but it's a little awkward to write if lit_tt and something else, then blah blah blah. Okay, lit_tt is not a very nice notation for the literal value true. It's really what we would call abstract syntax, which is the syntax that is generally used by a computer, but it's not the best way to present syntax to human beings. So I'm now going to introduce a sort of a two-level notion of syntax, a notion of abstract syntax. That's really the fundamental syntax of a language. And then a notion of concrete syntax, where we define some friendly notations for otherwise kind of ugly abstract syntax representations. So here's what I'd like to do. I'd like to have a shorthand for this lit B notation here. And so here's one way to do that in Lean. I use this keyword notation. And then I simply define, I can essentially overload one of the existing notation mechanisms in the Lean language, like plus operators, times operators, divide operators, square bracket notation for lists. I can redefine what those notations mean for my own types of objects. So here the notation that I'm going to use is a notation in Lean that uses these funny angle brackets, and you type them by backslash left angle bracket and backslash right angle bracket. Okay, and the idea here is that if I put a Boolean value between these angle brackets, I want that to be a syntactic sugar, a concrete syntactical notation for this term here. And you can see that Lean has accepted this notation definition over here. Okay, and so let's go over to our test file and see what we could write instead of this sort of stuff here. What I'll do is I'll make another copy of this, and instead of writing p eval, this term here, lit tt, what I'll do is I'll replace that with the use of these angle brackets like this. And now the key is that that is syntactic sugar for this. And the Lean compiler, it's really called an elaborator, the Lean elaborator, when it sees this notation here, it says, oh, self, I think Kevin defined what angle brackets with a B inside mean, and it's lit B. Okay, so in other words, this is just a syntactic sugar for this. And similarly, I can do like that. And here, this evaluates to true, and this evaluates to false. Good. Okay. And so here we have really the fundamental elements of almost any human usable formal language. We typically have an abstract syntax, a concrete syntax with syntactic sugars for more complex functional style programming, desugared terms. Okay, and we have a semantics. Okay, good. So maybe stop right there and let this sink in. Go have a sip of hot chocolate or something. Come back, think about what we've done, and then we'll be ready to move on to the next step. Okay, so pause your camera. Let your brain cells sort of settle down, and we'll come back and we'll do. How about we do connective based expressions next? Okay. Okay, we're back. Here we go. Okay, so good. So we have a very, very, very simple language here in which we can, define expressions. So let's, define an expression. We'll define E1 of type pexp. And there's not much that we can do here, right? We can define literal tt. We can define E2 to be literal, and in the first case, I include an explicit declaration of the type of E2, of E1 rather. Here I'll just leave it out since it can be inferred. Okay, so there. E1 is literal true, E2 is literal false. I can, of course, evaluate the application of p eval to E1 here and get true. I can apply the p eval to E2, and I'd expect to get false. And you'll remember that the way that these evaluations work is p eval applied to E1 rather. E1 is a, call it a variable in Lean. To evaluate a variable, you replace it with its meaning, so that's this. So this expression reduces to p eval tt. This TT then gets desugared into lit TT, so this is P of L lit TT. P of L lit TT works by pattern matching. Lit matches with lit, B matches with TT, and we return TT, and that's how this works. Okay. Good. Okay, so connectives. Suppose that we wanted to be able to write and compute the meanings of more interesting expressions. So, we know, for example, that in Boolean algebra, and as I've explained in propositional logic, those two formalisms being isomorphic to each other, that we have a notion of operators in the syntax of our language and corresponding operators in the underlying Boolean algebra. So let's implement a propositional connective called and actually to emphasize that this is a connective and not a Boolean function, I'm going to call it p-and, okay, for propositional and operator. And the idea here is that this operation will take two arguments, each of them being smaller expressions. So we have E1 and E2 of type px. Given those two expressions, E1 and E2, this syntactic expression constructor, p-and, given E1 and E2, glues them together into this bigger term called p-and E1, E2, and that bigger term itself we will treat as an expression in our language. Okay. So there you go. That is the sort of canonical way of implementing a binary sort of expression builder in the syntax of a language. And while we're at it, let's go ahead and let's also implement a connective called p-not. This will implement a kind of a unary connective that takes any expression, we'll call it E, of type px. Okay, and if we have any expression E of type px, then p-not E is a bigger expression of type px, a bigger expression in propositional logic. Okay. In fact, let's just do these one at a time here. I'll comment this one out for now. We'll come back to it in just a second, because what I'd like to do is I'd like to go down and now that we have our concrete syntax here, let's go over to our test file and use it. Let's sort of test abstract syntax. Let's test our abstract syntax for the not. Okay, given any expression E, we ought to be able to build a bigger expression, p-not E. So let's define, I'll just call it E3 of type px colon equals p-not, okay, applied to any smaller expression. Well, E1 is a smaller expression, so how about if I just put E1 here, and that works just fine, okay? That works just fine. What's really interesting, of course, is that I can define E4 to be an even bigger expression, okay, by, well, since P3 is an expression, I can put P0 followed by any expression. P3 could be, E3 could be a smaller expression, and so there's an even bigger expression, which I can think of as P0 of E3, but E3 is really P0 of E1, so this E4 is really P0 of E1. And E1 is TT, which is really just lit TT. So if I expand PE4 out completely, it's P0 of lit TT. Okay. Let me write that out as P5, rather as E5. And here I'll leave off the explicit type declaration, and I'll just write this as P0 of something. And in the parentheses goes a smaller expression. That's this P naught is this P naught. E3 is P naught of E1, so here's P naught, and here's where I put E1. E1 is this, but this is simply a syntactic sugar for this, and so here in parentheses I need lit TT, and I have no type errors. So this term type checks as being a syntactically valid term in our language. So this is the complete abstract syntax for E4, kind of expanded out. These two terms really are equivalent to each other. Okay, so by simply adding a new constructor to our syntax, I can build now an infinite collection of terms. Okay, here I had a kind of base case for one of two possible literal terms, but with this inductive definition, given any expression, I can always put a P naught in front of it to get a new expression, and I can put a P naught in front of that to get a bigger expression, and then I can put a P naught in front of that to get an even bigger expression ad infinitum. So now with two lines of specification here, I have a syntax that includes an infinite set of terms in propositional logic. Okay, so let's think about concrete syntax, and then we'll move down and repair our semantic definition, which is now missing, as you can see from the error message here, a specification of how to evaluate a negation in propositional logic. A negation being an expression in which P naught is applied to a smaller expression. Okay. Now, as you learned in the last lecture, the standard notation for not in propositional and in predicate logic is this sort of angle iron character. Okay, so we will define a notation where in angle iron E, or not E, is sugar, syntactic sugar for P naught applied to E. Okay, so wherever we run into this in our test file, it will be desugared to P naught E. Okay, so let's see how that works here. We might define E6 to be not of not, whoops, backslash not, that's lean syntax, of, and here we will use our syntax for literals like that. And let's get rid of these parentheses because they're unnecessary, and there you go. There's E6, okay? That's our syntactic sugar for this term in abstract syntax, not of true. Pretty nice, right? And finally, let's give a meaning to a term like this. Okay, and this is where that recursive thinking comes in. We can build up new terms inductively, and what we do to evaluate them is we break them down recursively and evaluate their subpieces and compose answers from answers for those subpieces. So in our semantics, if we get as an argument to p-eval an expression of the form P naught E, well, what are we going to do? What do we need to return? Clearly here we need to return some value of type bool. Let's suppose that E is lit true. Well, lit true means true, and we want not applied to true to mean false. Ah, okay, so there it is. There's the idea. What we need to do is we need to apply B naught, the Boolean operator for negation, to some Boolean value. And the Boolean value that we want to apply B naught to is the result of evaluating E recursively. So right here you can see we need a Boolean value, but we have in our context, we've assumed that E is itself a propositional logic expression. P naught E is the bigger logical expression, and we want to return the negation of the meaning of E. B naught applied to, well, not the meaning of, we can't put E here because it's not even the right type, right? B naught expects a Boolean argument, but E is an expression in our language. E is syntax. What we want to do is we need to have a Boolean value here, and the idea is we're simply going to evaluate the meaning of E to get the Boolean value that we then negate, and then that's going to do the trick for us. Okay? And so recursively, then, we're going to apply p-eval to the smaller expression E from which the larger expression not E was built. We evaluate E, we get a Boolean value for E, and then we invert it, negate it, using the Boolean operator B naught. Nice, right? Okay. And so now, let's see what happens over here. What do we expect when we evaluate E6? Not of true? Well, not true should have, well, let's see. This TT, literal, should evaluate to true. If we negate that with this first not sign, we get false. If we then negate that with this second not sign, we get true. So this whole thing should evaluate to true. Let's just test that by evaluating the application of p-eval to E6. And sure enough, there's true. And in fact, we could evaluate the application of p-eval to not E6, and we should get false, and sure enough we do. We just knew that that's the answer that we were going to get because of the way we've built up this logic. Okay, so cool. Now we have a logical language with literals and a single unary connective, unary because it takes only one argument, p naught. We have a nice concrete syntax for that unary connective negation, and we have a semantics that tells us, what an expression with a not sign before it means. And what it means is the negation of what the expression itself means. Okay. Good. Okay, so now let's do and. Okay. Let's add an operator to our language for p and. A connective to our syntax, p and. So if E1 and E2 are now propositional logic expressions, then and P1 and E1, E2 is an expression in our language. For concrete syntax here, we'll simply use the standard syntax that you will see in any textbook on logic, and that is to say, if we see an expression of the form E1 and E2 in our that's \and to get that and sign, that we will de-sugar that into this p and E1, E2. Okay, cool. Now, of course, we're missing a semantics for the and connective. So let's complete our syntactic definition here. If we apply p-eval to an expression of the form p and E1, E2, p and E1, E2, okay, then what do we want to return? Well, what we really want to return is the Boolean conjunction of the meaning of E1 and the meaning of E2 respectively. So if E1 is some big old expression that evaluates to true, and E2 is some big old expression that evaluates to false, then we want to return the Boolean and of the meaning of E1 true and the meaning of E2 false. The Boolean function and applied to the meaning of E1 and the meaning of E2 being true and false would return false. So the answer here is we want to apply the Boolean function or the Boolean operator. In lean it's called b and to two Boolean values. Okay, so we can put the underscores here to get some holes in our definition. Okay, so we're in a context here where we have a function that we can call, an evaluation function, giving it an expression and getting back a bool. We have two expressions, E1 and E2. So in principle, we can apply p-eval to E1, we can apply p-eval to E2, and in each of these holes we need a term that ultimately reduces to a value of type bool. And you can see what the answer is. You just stop the video right there for a second, and what are we going to do? Well, just like here, we evaluated E and then applied a Boolean operator to the result. We're going to do the same thing here. P-eval E1, okay? We're going to evaluate E1 to get a Boolean value. We then want to evaluate E2 to get a Boolean value. And so the interpretation, good. And then because the term, the syntactic term, uses an AND connective, we want to combine or compose the answers for the sub-expressions using the corresponding operator from the semantic domain of Boolean algebra. And that function will be the Boolean AND operation. So I'm going to leave a little hole here for you to fill in. Okay? Nice. Okay, and since we're on a roll here, let's go ahead and add an OR connective as well. Okay, so instead of P AND, we will add a P OR connective to our language, and after we do this, we'll come and we'll build some more interesting logic over here in the test file. Okay, so there is the addition of our new OR connective. We'll define a notation for OR, and it looks just like the notation for AND, except we'll now use the \OR concrete notation, and E1 or E2 will desugar to P OR E1, E2. Okay. And now, of course, we need a rule that tells us what to return when we evaluate P OR E1, E2. When we evaluate a propositional logic expression of the form P OR E1, E2. And the difference here is that we're going to apply the Boolean OR operator rather than the Boolean AND operator to the results of evaluating the sub-expressions. Okay, and so here I'm going to leave two holes for you to fill in. Nice. Okay. Well, shoot. Let's make one of these work. You know what the answer is here anyway. Before I fill in the answer here, you do it? Yeah, good. There you go. Okay, so to evaluate P AND E1, E2, we evaluate E1 to get a Boolean value. We evaluate E2 to get a Boolean value. We combine those two Boolean values using B AND, which is the semantic meaning of the syntactic connective AND. Now this is actually really nice, right? Because at this point we have something that is pretty darn close to a complete little language of propositional logic and or you could also think of it as a language of Boolean expressions. Okay, so we can define, for example, the following. Let's say, what are we up to, E6? Let's define another expression, E7, to be, how about E6 and E5? I don't even know what what that is. Well, okay, E6 is not true, and E5 is not true. Okay, well, so this is true. This is the same as this, so this should evaluate to true. And here we're computing true and true. And if we evaluate E7, do we have a rule for evaluating AND connectives? We do. So presumably, if we evaluate E7 here, we should get true. We can evaluate that because our definition over here is fully correct, and in fact we do get true. All right, what if we evaluate E6 and E5, and how about we'll put a false literal in here, like that. Okay, if E7 is this should evaluate to false, because whether E6 and E5 are true or not, anything and false should be false, and sure enough, there you go. Okay, so, I mean, sit back and sort of take stock of what you've got here. You have the ability to write logical expressions using ands, ors, and nots, and you have a semantic evaluator that can take an arbitrarily complex expression in this language and reduce it to a Boolean value. So you have a semantics for this language. That is pretty nice. Okay? Good. The one thing that we're missing in our implementation of a language of propositional logic so far, or of useful Boolean expressions for that matter, is the notion of propositional logic variables. Okay, in arithmetic expressions, variables mean numerical values. In Boolean algebra, variables mean Boolean values. In propositional logic, variables mean Boolean truth values. A variable, the interpretation of a variable is that it either means true or false. You can think of a variable as a proposition. It's an expression itself. And as such, it is either true or false. And that's all there is to it in propositional logic. Okay, so let's go ahead and add a notion of variables to our syntax. Now, first I'm going to do it in a way that's not going to make any sense. Okay, I am going to add 3 variables, and I'm going to call them x, y, and z. Okay, let me fix my typos here before I go any further. Good. Okay, and we'll add one more syntactic construct, z, another variable. And we will understand that, we'll call these variables. Really, they're just expressions in our language, and that's all that this says. Okay, but we need to have now a way of interpreting what x, y, and z mean. So I don't need to do anything in terms of concrete syntax here. These are perfectly nice ways of writing these variable names here. Okay, but I do need to extend my my semantics to explain what it means when I see the variable x. So I could write something as simple as this. If I get the expression x, well, let's suppose I want x to mean true, y to mean true, false. So x is true, y is false, and z is true. Okay. I could say if you get an expression, if you evaluate a variable, the variable expression x, return true. Okay. If you evaluate the variable expression y, return false. If you evaluate the variable expression z, return true. Okay, and this works just fine. Okay, so over here, I can now write things like this. I can evaluate the application of p-eval to x and y. Awesome. Okay, so let's see what happens when I do this. I run p-eval. px, the argument, is x and y. So that matches with this expression. Remember, x and y just desugars to p and e1, e2. I evaluate e1. e1 is x. Recursively, I evaluate x. That returns true. So this expression returns true. I evaluate e2. e2 is y. Evaluating y recursively returns false. So I get a false here. And then I apply b and to true and false, and I get false. and that's what I have as an answer right there. Okay? It works like a charm. And I can write, or, not Z, and everything. Let's see what's wrong here. Okay. I think I just need parens around the whole expression here. Nope. Let me see. Okay, let me put this aside for just a sec so I can just continue. I'll come back. We'll come back and debug that in a minute. It's good to be able to debug these kinds of things anyway. Okay, so I can evaluate at least expressions like this. Let's see what happens if I try to evaluate p-eval not z. Okay, z evaluates to true, so this should evaluate to false. Let's see, what if I evaluate not z? Not z should evaluate to true. It does. Let's see if I evaluate x and not z. And this is where I run into a little bit of a problem. P and. Okay, let me not worry about it for just a sec. Sorry about that. I will come back and debug it in this video, and you'll appreciate that, we all have to debug things sometimes. Okay, so the point is that modulo this little glitch here, I can write logical expressions involving logical variables, and I can evaluate them. Now here's the problem with this solution for variables. I said in the introduction to this implementation exercise that we wanted, that we must really define propositional logic as a language in which we have an infinite supply of variables. So there's simply no way that I can provide an infinite number of variables by listing them, enumerating them as part of the syntax of my language like this. Okay, so X, Y, Z, W, Q, Kevin is from Charlottesville, Nifty is a cat, Greta is a dog, it's raining outside. There's just an infinitude of possible variable names, and I simply can't list them all here. Now, one solution to this problem is to provide a parameterized constructor. So instead of trying to enumerate all of these, I could just say, well, I'll provide a variable constructor that takes, let's say, n, a natural number, as an index, like this, okay? And now this gives rise to an infinite collection of what we'll think of as variable expressions, okay? So over here in my, this is no longer going to work. Over here in my test file, I could certainly define, well, let's say, let's call it x var. Let's just call it actually x is v 0. Okay, and we'll define y to be v1, and we'll define z to be v2. Okay, very nice, except I need a 2 here. This gives nice names to these otherwise kind of cryptic variable terms. So v sub 0, v sub 1, v sub 2, v sub 0, that's mathematician speak for the 0th v object. V sub 1 is the first v object. V sub 2 is the second v object. We call this argument an index. Okay, it's not the value of the variable. It is a unique identifier for what variable we're talking about. Okay, so v0 is one variable, v1 is a different variable, v2 is yet another variable expression, and all of this now works. Now, if we replace the x, y, z here with this notion of a kind of a parameterized variable constructor, well, of course we have to fix this stuff down here, right? And so in lieu of x, we say, well, if our expression is v0, then we'll return true. If our expression is v1, then we'll return false. So this is what we call x over here in our test file. This is the variable we're going to call y. Okay, and z, of course, is v2. And so we'll just put a little comment here to remind us that's what we mean by z. And now we can evaluate the application of p-eval to, for example, x. Okay. X is a variable expression in the syntax of our language. It's a term built by the v constructor for building variables, and we have a semantics for it. So p-eval x evaluates x to v0. P-eval of v0 is, well, the argument matches with this pattern, and we return true, and so we get a true here. Okay, good. So this is one way to introduce variables into our language. Now let's just make sure that when we evaluate y and z, we're getting the values that we expect. So we expect x to evaluate to true, y to evaluate to false, which it does, and z to evaluate to true, which it does. Okay, so everything is now hunky-dory, almost. Okay, and the, well, there are actually sort of two almosts here. We see we still have an error here. Okay, non-exhaustive match. The following cases are missing. P-eval for v of the successor of the successor of the successor of something. Well, what this is saying is we have an infinite possible collection of v's here, and we don't have a definition for, the term v3 or v4 or v5 or v6 or v7 ad infinitum. So to give a complete definition of the semantics here, we need to have a default return value for any other variable term. So we could write that like this. And we have to return a value of type bool here. So we're just going to return false for any of the variables that we don't happen to care about in our application. Okay, but we can still evaluate them over here. We can still evaluate, for example, p-eval applied to v5. Okay, v5 is a term in our language, and what's it going to evaluate to? Well, by this rule, which matches on any expression v followed by any number other than 0, 1, or 2, returns false, and so here we have false. Okay, think about in Java, for example, if you start up a program and have some int-valued variables that you haven't initialized, they're just initialized to 0. This is kind of like an initialization or a default value for all of the other variables in our language. Okay. Cool. So take a minute, pause the tape. This is a lot to digest. Pause the tape and think to yourself, okay, what's wrong? What's still wrong with this solution? And I'm going to give you a minute to think about it. Okay, the problem is that our variables can't vary. We've hardwired the values of x, y, and z, of v0, v1, v2, and indeed of all other variables. We've hardwired those values of these variables directly into the semantics of our language. We really don't want to do that. This is a language in which x always means true, y always means false, z always means true, and any other variable always means false. The whole point of a parameterization, of having a variable in an expression, is that it can take on different values at under different circumstances. Under some interpretations, we might want x to evaluate to true, and under other interpretations, we might want x to evaluate to false. And so we need a different approach here. And here's the approach that we're going to take. We're going to take these rules for evaluating the values of these variables out of the evaluation function, and we're going to put them into a function that we'll call an interpretation function. So we're going to define an interpretation function, and we'll call this, interp1. Okay, this is going to be a function that takes, we want to say that takes a variable and returns its value, but how do we say that it takes a variable? A variable is just one of several possible kinds of terms in our language here. It's not quite, I'm going to put, question mark. We want to take a variable and return a value of type bool. But what's a variable? We don't have a type variable in our language. And so here's what we're going to do. We're going to take this constructor out of the syntax, and we're going to have a separate data type just for variables. And I'll call it var. That's what we've called it in some of our other implementations. Var is a type, and we'll just have one constructor for var, and it will be, here, I'm going to paste this material back in down here so I don't lose it from my cut and paste buffer. We're going to take this constructor out of the expression type and put it here like this. Okay, so we now have the ability to build objects of type var in addition to building objects of type px, but we still have no variable expressions defined here. So let's use what we've got here. We've defined a type var. Here we have an error now. Let's comment out this code block, and we'll cut and paste it and adapt it. Okay, so here's the end, and now here it is again. I want x, and I'm going to call this maybe x var, of type var to be v0. Okay, well, we need to open var here, and we need to open var here, and now we can use the constructors defined in the var namespace, namely v, and so there we go. Okay, and now x var, let's call this y var. You'll see why I'm doing this in a minute. And let's call this z var. These are now variables. Okay, so we're not going to pay any attention to that stuff yet. We're focused here. Okay, so with this definition, we define these syntactic objects called variables. Okay, but we've seen this before, but stick with me. So, but we need to incorporate variables now into the syntax of our language, which is defined by this propositional logic expression, or px type. And so I've got literal expressions here. I've got various operator or connective expressions here. And now I want to build a notion of variable expressions here. And a variable expression is going to be built by a constructor called var, and it's going to take an object of type var as an argument and give me back, here we'll put v of type var here like this, and that gives me a propositional logic expression. Now you'll notice I've done something a little bit worrisome here. I've used var as both the name of a constructor and as the type of v. Lean is smart enough to disambiguate, so it understands that px.var is this, and is px.var is distinct from var being this type here. Okay, so now I have a syntax that supports literal expressions. A literal expression is essentially kind of like a wrapper around a Boolean value. A variable expression is kind of like a wrapper around a variable. And now we're pretty much good to go. Well, until it comes to the question, well, you know, how do you evaluate a variable expression? So let me cut and paste this stuff down below, a little bit like this. Move this stuff along so we can focus on our evaluation function. We have an error here, and it says non-exhaustive match. The following cases are missing. I don't have a semantics for what to return when an expression is a variable expression. So I need a rule so that if an expression to be evaluated is of the form var, that's the constructor, vn, where n is the index of the variable, then I want to return a Boolean value. Okay, and what Boolean value do I return? This is a little bit tricky, right? This is the trickiest part of this whole thing. If I evaluate an expression, it can be a literal expression, which is a wrapper around a Boolean value, in which case I just return the wrapped Boolean value. If it's p naught e, I evaluate e and return its negation. If it's and or applied to two expressions, I evaluate those expressions and return the and or the or of the results. If I get a variable expression like x being var v0, what do I return? Well, the answer is it's not clear here what I return. In the preceding example, what I wanted to return for x, let's go and look at what I cut and pasted from my previous work. I really want v0 to evaluate to true, v1 to evaluate to false, v2 to evaluate to true, and all the other variables to evaluate to false. So I'll put an otherwise here. Okay, so what I'm going to do is I'm going to define a function. I'll call it interp1. And this is an interpretation that's now going to take any value of type var and return a bool. Okay. Okay, good. So we're here where we have now got a little bit of a problem with our namespaces, and I'm glad we've run into this. So I have two types here, one type called var and one type called px with a constructor called var. Okay? So the type name var is in my global namespace, in my available namespace, and because I've opened px here, var is also visible. So when I say var out here now, it's not clear whether it's this var or this var. In this case, the context completely disambiguated what I meant by var. This is a constructor name, and this has to be a type name. So this has to be this var, and this var here is my constructor. But now if I check var out here, I'm going to get a little bit of, I should get a little bit of an error. Let's see. Whoops, I put it before the open px. If I check var here, I have no problem because I haven't opened this namespace. So var is this type name up here. But after opening px, I run into a problem because var has multiple possible interpretations, either the type var or the constructor px.var. I can simply disambiguate that by saying, for example, this I mean px.var. So I can always add a prefix using dot notation to disambiguate cases like this. And that's what I'm going to do down here. So I'm going to say we can take any Yeah, um, it's a little bit more complicated than that. So let me just change the name of this to variable. I'm going to change my type name to variable. We'll just hack our way around this problem. Okay. And of course, variable is a reserved word in Lean. So we need a different name here. So let's see, what should we use? How about varby? Okay. It's a crappy name, but we'll just call variables in our language varbies. We're going to open varby here, and this has to be varby, and there is no longer something called var outside of the px namespace, and good. Okay, so here we are now defining an interpretation that takes any variable, a value of this type varby, and returns a bool. And look, here's the definition of my function. If the variable that I get, a value of this type, constructed by the application of the v constructor to an index value, a natural number, if the variable I'm given is v applied to 0, I return true. If it's v1, I return false. If it's v2, I return true. And if it's any other variable, then I return false. So we're almost there. Now the question is, when I get to this p-eval here, I'm given an expression. If it's a literal value, I know what to do. If it's a connective expression, I know what to do. But if it's a variable expression built by the var constructor in my language syntax definition, in other words, if I'm getting a value to be evaluated like var v0, what do? Suppose I get var v0 here. Well, I mean, I could, call this function interp1, but then I'd be hardwiring this set of values into my semantic evaluator again, and I'd still have the same problem that I had a minute ago. So the trick then, and you've seen this before, and most of you already know what's coming, is what we need to do is we really need to pass an interpretation function like this one, but not necessarily this one, as an argument to our evaluation function. So we're going to pass in a second argument to our semantic evaluator, that second argument being some interpretation function for the variables. And that interpretation function is going to be of this type. It's going to take any variable and return a bool. So there we go. p-eval now takes an expression and an interpretation like this function that we can use to look up the Boolean value of any variable. So p-eval takes an expression and a way of discovering or looking up the value of any variable. And given those two pieces of data, an expression in propositional logic and an interpretation will return a Boolean value. Good. Okay. Awesome. So what's wrong with our first line of code here? Well, the problem is that our function p-eval now takes two arguments, but we're only pattern matching on one argument. If the argument is a literal expression, it doesn't really matter what the interpretation is, right? Because a literal expression doesn't contain any variables. And so we can just ignore that first argument. We can use an underscore to match any value here. And we don't need to give it a name or destructure it and look inside it and see what that function is, even if we could do such a thing, because we don't use that interpretation function to figure out what result to return over here. Now, similarly, every one of these other rules now needs to have a left-hand side that matches on two arguments. So if we get an expression p not e, we need an argument for the interpretation. But now we can't just leave it nameless, because in order to evaluate p not e, we have to evaluate e, and e could be any expression. And as any expression, it could contain variables. and we'll need to be able to evaluate those variables. So we're going to need an interpretation to evaluate any variables that might occur in E. So here we'll give a name, we'll just call it I, to the interpretation value that's passed in as a parameter to p-eval. Now over here, when we want to evaluate p0 applied to E under the interpretation I, we evaluate E under the interpretation I. Aha! That returns a Boolean result, and we take the negation of that, and that's our answer. To evaluate P and E1, E2, we need an interpretation, I. That I will match the value of this function that's passed in. And to evaluate the expression and E1, E2, we will evaluate E1, but we now have to do it under the given interpretation, I. Right? P-eval now takes two arguments, so there's the expression argument and the interpretation argument. Similarly, we need to pass that interpretation value to the second recursive call to p-eval, and then we're good to go. Here, to compute OR, we need to do the same thing, and I'm going to let you fill in these values here. And now finally, we're down here, where if we're evaluating a variable expression of the form var v, and we can just, I think, just call this v for being a variable, then it's px.var v. Let's move this rule up to just after lit. Good. Yeah, I see. Let me undo that. We have to evaluate a variable again with an interpretation. So we add an interpretation argument here. So our expression is var v, where v might be something like v0, v1, v2. We have this interpretation I. Okay, and now what do we do? And you know the answer because you've seen this before. We have a variable v that's wrapped up inside our variable expression, var v. Var is a wrapper for a variable. The var constructor wraps a variable v. An expression can be a variable expression that looks like var wrapping a variable v. We have a function here that, given any variable, returns a bool, so we can return the right value by applying that interpretation function to the variable v. And then, finally, we're done. Or almost done. Okay? Awesome. Okay, so I can delete this little note here because I've implemented this particular interpretation function right up here. And now I think that we're in pretty good shape. So let's go back over to our test file. We defined a couple of variables, xvar, yvar, and zvar. We changed the name of var to varb. We have to open this namespace varb that exposes the definition of, or the definition of this constructor v. Okay, so here are our variables xvar, yvar, and zvar. Remember though that these are values of this variable type. These are not expressions in our language yet. So if we tried to evaluate the application of p-val to xvar, for example, we're going to get a type error. P-eval expects an argument of type px, but it's given a value of type of varb variable. Okay? To evaluate, to turn this variable into an expression that we can evaluate, why, we need to apply the var constructor to it, like that. Now we're applying p-eval to var xvar. Xvar is v0. Var v0 is var v0. So that's good. And what do we get here? And we get some crazy answer. So what's the problem here? Well, this is a partial evaluation. We're evaluating p-eval applied to an expression, but really to get a result, we need a second argument here, an interpretation. Aha! Okay, so let's take this interpretation over here because it's sort of really more of a test example than anything else. We'll put that interpretation right here in our test file, and we'll pass this particular interpretation to this evaluation expression. And now it's going to work. What's the value of var xvar? This is a variable expression in our language. Okay, under interp1. And what interp1 says, well, let's evaluate this entire expression here. We're applying p-eval to two arguments, var xvar and interp1. Var xvar matches this, where var matches var and v matches xvar, and where xvar is defined to be v0. So really, this is the same as if I had said xvar v0. Okay, so we can just make sure that you see that those are equivalent, and maybe I'll just write those on two different lines, right? So xvar is really just defined to be v0, the 0th variable. These are the same. If I evaluate xvar or v0 under interp1, what do I get? Okay, so let's take this again. We apply p-eval to these two arguments. I have var v0 here. Var matches var v0, where this little v matches v0. I matches interp1. Okay, and the result I return is the result of applying this interpretation function I to v0. Okay, and here's the answer right here, true. Okay, so this is how we implement the notion of a sort of an infinite number of variables giving rise to an infinite number of possible variable expressions, one for every variable in the language, and how we can then evaluate variable expressions. And this then is the general form of an evaluation function of a semantics for propositional logic. A semantics assigns a truth value, true or false, a Boolean value, to a proposition given an interpretation for the variables that appear in that propositional expression. Okay, very good. So we can clean up our language a little bit more, maybe by defining some some sort of new notation for maybe variable expressions. Let's try this and see if it works. We'll say a notation with square brackets v that reduces to var v. Yeah, I think that. Yeah, let's not try this here. I'll come back later on, maybe not, and won't fix that. The answer is really that we can give nice names to variable expressions in our language. So let's go ahead and do that. Let's take this over here, and we can define x now as a variable expression. So this will be of type px, and we'll define this to be the variable expression, let's say var v0. Okay, so x is now a variable expression that we can use in our language, and this is the kind of underlying complicated abstract syntax for this thing. And we'll define y to be var1 var of v1 and z to be var of v2. And again, this is just what we've already done. Okay. Go back and look at the lecture for arithmetic expressions. Essentially the same thing. We're just applying it in a different way here. Okay, beautiful. Okay, so now what can we do? Now we really are cooking with gas, as my old math professor used to say. So now we can write propositional logic formula like the following. So where are we? E8. Let's define E8 to be, x. That's an expression now in propositional logic in our implementation. We can check that by making sure that that's of type pexp. Okay? So there you go. We can define E9 to be x and y. It type checks. Okay? We can define E10 to be not x and y. Pretty interesting, right? We can define E11 to be not x and y or z. Aha! You have now, or we have together, defined the syntax, in particular the concrete syntax, that logicians and mathematicians would use every day to write expressions in mathematical logic. And we have an interpreter that interprets the meaning of these expressions under any given interpretation. So for example, I don't know what the meaning of not x and y or z is. I could figure it out. Maybe we should do that, but we could evaluate it automatically here. So let's see if we can figure out what it is. X under this interpretation evaluates to true. Y evaluates to false. So x and y evaluates to false, and not false is true. So this is true or something. Z happens to evaluate to true, so this is true or true. So this should evaluate to true. So we can evaluate the application of our semantic evaluator to E11, and we should get true. And why do we get this complicated? Why do we get this complicated thing? Think about it. Think about it. Okay, you got it. Because we're not fully parameterizing p-eval. P-eval not only takes an expression, a proposition in propositional logic, but the semantics of that proposition is not defined without an interpretation. So we have to provide an interpretation. So we can provide interp 1, for example. It's the only one that we've got here. And what happens here? We get an error message saying, trying to evaluate sorry. Sorry is another way of writing a hole in a program. Here I could write, sorry, I'm not going to tell you what goes here. Sorry, I'm not going to tell you what goes here. And we can't actually evaluate or reduce an or expression to a result because we have holes in the definition of our function that still need to be filled in to have a complete answer here. So we expect, I think, you can confirm this, but I expect that this will return true. Okay? But you won't know until you complete the definition of this rule here. Very nice. Okay. So at this point we have a concrete syntax for propositional logic, and we have most of a semantic evaluator with some remaining holes in it. Pretty cool. This is how we build programming languages, among other kinds of languages. This is how, in fact, we build logics. This is how we specify the syntax and the semantics of a logic. And there are many, many, many logics in computer science. This is a particularly simple one for which we can write a semantics as a function, as a total function. one that gives an answer for every possible expression, syntactically valid expression in a language, as long as you also provide an interpretation. For more complex logics, that's not the case, but we're not going there at this point. Okay, so there's one last little piece of our definition that I'd like to talk about, and it will get us to a really beautiful formulation of the syntax and semantics of our language here. Okay, and here's the idea, and this is where I'm going to leave you with a homework for this test. Here we have a unary operator, a unary connective in our syntactic definition. Here we have two different binary operators. But as you know, there are other binary operators that we use in propositional and in predicate logic. So one of them is implies. And, we could call that, p-imp, for example, could be the name of a constructor to represent the implies connector in logic. And another one is equivalence, or also written as if with two F's and pronounced if and only if. So we'll write that as p-if, like that. That will be the name of the constructor that we'll add here. Okay. So, good. Now, here's the problem. Every time I add a new connective, I need to change my syntax definition by adding, for example, a new constructor. Let's go through a little bit of an exercise here. We'll do this for p-imp. So implies is a connective that takes two smaller expressions and constructs a larger expression, like that. Okay. And now I need to go down here and I need to update my semantic definition, because now I have p-imp as a possible syntactic form, E1, E2, like this, I : equals, and then I write some stuff over here to return a value for the expression E1 implies E2. I'd need to do the same thing for P if and only if. In fact, I'm going to let's just go ahead and do this like this, and the rest of this line basically looks the same. The form of all of these binary connective expressions is basically the same. It's some binary connective followed by two smaller expressions. And again, I have to come down here and fix this as well by adding P if and only if here to the semantics. Okay. So it's a little bit unfriendly to have to change my core syntactic and semantic evaluation functions whenever I add a new connective to the language. So what I can do is I can actually kind of factor out these names and replace them with a single kind of generic operator expression. So here's the idea. I'm going to introduce a new kind of operator here. It's just going to be propositional binary operator, okay, which could be p-and or p-or p-imp or p-if. And it's going to take two expressions, as usual. It's going to build a larger expression, but what it's going to take is, we'll call this C for connective. We'll call this binary connective. How's that? bcon. Binary connective, and like this, okay, where bcon is yet another type. Here, I'll call it like this with a small b. Binary connective. Okay, and I'm just going to have now an enumerated list of values of this type. One will be called p naught, p and, p naught is not binary, p and, p or, I'm doing your work for you, p implies, and p if and only if, like this. I called this com, and I meant con for connective, C-O-N-N. Yes, good. Okay, and the idea now then is that instead of p and E1, E2, I write p bin con, p and E1, E2. Instead of p or E1, E2, I write bin con, p or E1, E2. So I can comment out all of these constructors, and there I'm just left with this. Okay. Very good. So now, good. Let's fix up our definition of our concrete notation. So instead of writing p and E1, E2, I need to write p bin con, propositional binary connective, p and here. P and is not defined because it's not visible because I haven't opened this namespace. Let's open that namespace. And now look, there we go. So E1 and E2 now desugars to p bin con, p and E1, E2. Awesome. The same thing will be done here. P bin con, or p or E1, E2. Very good. Now, what do we have down here? We have to fix up our semantic evaluator. Right? So instead of having a term p and E1, E2, I have p bin con, p and E1, E2. And I'm now good again. I'm going to move my definition for my semantics for variable expressions right after lit. So I have literal expressions, I have variable expressions. I'm going to move my definition for the not operator down to the bottom like this. And now, well, I have a bunch of lines here for the different cases where different binary operators are being used. Okay, so we're going to come back and fix this in just a second. Okay. Replacing, so here we managed to replace 4 lines of, and potentially more lines of syntax definition with one parameterized line, a line parameterized by binary connector, which is either and or implies or if and only if, the same as equiv or equivalence. Okay, but down here we have like 4 different rules here. Okay. And what I'd really like is just one. Okay, so instead of those 4 rules, what I'd really like to be able to do is just write p bin con. And now, instead of matching on a term that's defined in our namespace, I'm going to use an unused variable to match on any term of type bincon. Okay, so I will just call it con E1, E2. Okay, so now what do I return? If I get an expression of the form pbincon and one of these values, like pand or por or pimp or pif, followed by E1, E2, well, what do I return? Well, all of these answers down here are going to be kind of the same, but how are they going to vary? They vary in terms of the Boolean operator that I apply. And the Boolean operator that I apply here depends on which connective is used in my expression. So if the connective is pand, then I use band. If the connective is por, I use bor. If the connective is pimp, well, I need to use something over here that implements the Boolean implies operator, right? And the same here for if and only if. Aha. Okay, but all I have to work with here, if all I know is that I've got an expression of the form pbincon using some connective con, E1, E2, I know that I need to apply some Boolean operator here to two Boolean values. Okay? The Boolean values are going to be the values that I get when I evaluate E1 under the given interpretation, and when I evaluate E2 under that same interpretation, just like here. I need an interpretation argument here. Okay, so look at this. Here's a hole right here. Yeah, Lean's complaining because it doesn't like it when you use placeholders where functions go, but I can use it with you. You know that some function needs to go here. Okay? Some function needs to go here. And that function depends on which of the connectives is used as an argument or as a parameter here. So somehow or other, we need to take one of these values, which are our connective values here, and turn it into the appropriate Boolean function. Okay, and so I'm going to replace that underscore with an underscore in parentheses here. Okay, and I'm given this connective thing, but that connective here is a value of this bincon type here. It's not a function, it's just a piece of data. Here I need, though, a Boolean function, so somehow I need to take whatever connective I've got, pand, por, p0, whatever, it wouldn't be p0, it's binary connective, and turn it into a Boolean function. So here's the way to do that. And again, you've seen this before. Go look to see how we did this for arithmetic expressions, and what you'll see here is that we need a function that turns a connective or an operator name into the corresponding Boolean, or in the previous case, arithmetic expression. So I'll call that interp con. Okay, interp con. And this function interp con will take a connective and return the appropriate Boolean function. Now, we haven't defined that function yet, so let's define it here. We'll define interp con to be a function that takes a value of what type? Bincon takes one of these values, pand or por or p0, a binary connective, and returns what? A binary Boolean function. Okay. So it's going to have to return a binary Boolean function here. Now, how do I write the type of a binary Boolean function? Well, a binary Boolean function is a function that takes a Boolean value and then it takes another Boolean value and it finally returns a Boolean result. Okay? So interp_com is going to interpret, is going to give us the interpretation, I'm sorry, I wrote it using ems again, con. Interp_con is going to take a binary connective, a piece of syntax like and or not, and return the corresponding Boolean function. So this function gives us the semantics of the connectives in our language. P_eval gives us the semantics of an expression in our language, a Boolean value. This interp_con function, actually let's call it C_eval, okay, for evaluating a connective. Takes a binary connective, and it's a binary connective, so I'll call it C2_eval, okay? How about bin C_eval? Binary connective eval takes a binary connective and returns a Boolean function. Okay, so let's write one line of this. If the connective is P and, then what function do we want to return? If we are evaluating an expression built using a binary connective con, connecting E1 and E2, what function do we want to apply? What Boolean function do we want to apply to combine the Boolean results, the Boolean values of the sub-expression? Here, let's fix this. Interp_con is now bin C_eval. Okay, good. And the answer is, if the connective is P and, we want to return the Boolean function B and. And I bet that you can guess that if the connective is P or, that we want to return the Boolean function B or. Okay? If the connective is P imp, we want to return a Boolean function that implements the implies Boolean function, but there's not one built into Lean, so that's a hole that you're going to have to fill in. So you can fill in that hole by defining a Boolean function that implements the implies truth table. Okay, so that is a test problem. Okay, that's a test problem for you. Okay, and the same with if and only if. If the connective is propositional if and only if, also called equiv or equivalence, then here you need to return a function that implements the truth table, as it were, for the if and only if function. Okay, so you can define and you must define these functions here. So define, let's call it B imp for the, let's call it with a lowercase. We're going to define B imp to be a Boolean function, and we'll say it is of type bool to bool to bool. Okay, and here we will return B imp, and we'll use sorry to escape from having to implement it here, but that's something that you're going to have to do. Okay, and here we'll return a function called B if and only if, and similarly you will have to define this function here. So B if and only if, this will be a Boolean function that you'll define right here. Okay, so we started this lecture with the idea that propositional logic is a formal language that has a syntax inductively defined based on literal expressions, variable expressions, and constructors for building larger expressions out of smaller expressions using logical connectives. And, or, not, implies, if and only if, and so on and so forth. That gives us an infinite set of propositional expressions, but that's just syntax with no meaning. Then we said that the semantic domain for propositional logic is Boolean algebra. And what we meant by that was that every literal expression in our language means a Boolean value, has a Boolean value as its meaning. So p true means true, p false means false. Every variable expression has a Boolean value. But the value of a variable expression is defined not in the syntax or semantics of the language, but in an interpretation that is passed as a parameter to the semantic evaluation function that defines the semantics of our language. So a variable has a meaning under a given interpretation. Okay? And an expression has a Boolean meaning that's defined recursively. And here's the definition of the semantics of propositional logic. Okay? The semantics take an expression and an interpretation for the variables, an expression, and an interpretation that assigns a Boolean value to each variable and reduces that expression to a Boolean meaning under the given interpretation. Okay? That's terrific. Okay? If we get a literal expression, that's just a wrapper around a Boolean value, we return that Boolean value. If we get a variable expression and an interpretation I, we return the result of evaluating that variable inside of the variable expression by applying that interpretation function I to it. If we get an expression built using a binary connective with two sub-expressions, E1 and E2, under some interpretation I, we evaluate each of the sub-expressions under that same interpretation I to get two values, two Boolean values. Then we combine those Boolean values using a Boolean function that depends on the Boolean connective that was used. The semantics of the AND connective is be AND, the Boolean function be AND. So again, we're relating syntax to meaning. The meaning of the AND connective is the Boolean AND operator in the algebraic structure known as Boolean algebra. Okay? Syntax is a language like a programming language. Semantic domain is an algebraic structure, in this case Boolean algebra. And a semantics associates things in the syntactic domain with things in the semantic domain. Expressions here map to Boolean values here. Connectives here map to Boolean operators over in the semantic domain. Okay? Terrific. Okay? So test questions number 1 here are to fill in implementations for these Boolean operations. And the second thing that I'd like you to do is I'd like you to show that you understand all of this by implementing a notion of unary connectives. So inductive, uncon. So this is a unary connective, or you could call it a unary operator, unop if you want. But this is a language of logic in which the operators you think of as connectives that connect expressions into larger expressions. So it's an operator in an algebraic sense, where the algebra is an algebra of expressions, but we'll call it a connective because that's what people tend to call these operators when you're in the context of defining the syntax of a logical language. Okay, and so one of these unary connectives will be negation. Okay, so we'll call this P naught. Okay, so P naught is a unary connective, and what I'd like you to do is to flow the availability or the definition of this unary connective all the way through the language. So all the way through the rest of this file. Okay. Now there are other unary operators in logic, right? P naught takes a Boolean value and returns its opposite value. There's another one that we could call propositional logic identity. That's a unary operator that takes any Boolean value and just returns that Boolean value. Okay. Then there are two more unary operators in Boolean algebra. One takes any Boolean value and always returns true. The other takes any Boolean value and always returns false. So just as we defined binary connectives here as part of the syntax of our language, let's not do this one here. Let's just have a single unary connective P naught, because that's how people generally define propositional logic. There's a not connective. Okay, and let's just talk very briefly about how you're going to flow this through. Well, here you're going to need, in the syntax, you're going to need a constructor to replace P naught with a constructor that is like this, except it's a unary it's a propositional unary connective. So it's not a binary connective, it's a unary connective. Okay, and it takes not two but one sub-expression here. So just E instead of E1, E2. Okay, and with that you should be able to delete this constructor, replace it with a unary connective constructor that takes a value of this unary connective type, okay, as an argument, for which there's currently only one possibility. And you should be able to make that replacement. So do for unary operators, of which there's just one, what we've already done for binary operators, of which there are four. Okay, so I'm going to delete this because that's your job with a new P on con constructor. Okay. Very good. Okay. So that's a key issue. Okay. I'm going to delete this material here now because we don't need to look at it anymore. Okay. So this is a test question. Okay. Down here, I would like you to add notations for implies, using arrow, and for if and only if using this bidirectional arrow. Okay. And it's very straightforward. You just model your solutions on what we've done right here. Okay, let's try one just for the fun of it. Hey, look at that. Okay, very cool. I'm going to delete that. Okay, so test question. This is not hard. Okay, add notations, add concrete notations, concrete syntax. Okay, for implies using arrow, and for if using if and only if using, you know, this if and only if or equivalent or by implication arrow. Okay. These are test questions. implement these binary functions. Okay. Good. And finally down here, you're going to need to update the semantic evaluator function to handle p uncon expressions. Okay, expressions built using unary connectives, and this is a test question. Okay. There's one more little piece to this test that I'm going to put in a separate video that I'll post tomorrow morning. Okay. But for now, this is what you need to do. I am here for the rest of the week to help you. I will post hours where I'll be available each day for the rest of the week to help with this, and more details will follow in a class announcement on the class website via Colab. Okay, so that's it for now. One more little bit, but this is plenty to get started on, and the next bit won't require anywhere near as long of an explanation as this. Okay, so that's where we are. That's what you're to do. It's probably the case that if you followed along, you're already done. Okay, in which case you're done with the better part of the test already. Okay, so stay tuned for more shortly, and I'll talk to you again very soon. Thanks.